So I would like to call Mr. Tomasz Krysinski from Airbus Helicopters from the Aviation and Hydrogen section. And on that, I want to say that more than a decade ago, I happened to be...
Good morning to everybody. I hope
yes, good morning.
you
Okay.
hear me. I'm in Marignan.
Just go on.
My name is Tomasz Krysinski. I am Vice President, Director of Research Innovation at Airbus Helicopters. So I'm very happy to be with you today, and I will share you our passion for zero emission flight. As of course, hydrogen is one of key players. So just to show you how the revolution in aeronautics can come very quickly. You see here on the left side the New York City in year 1900, and we had only horses. 13 years later, you see only cars. In 13 years, we moved completely from one mean of communication to another one. And then main reason for it was really the pollution generated by horses. And now we live in the period where everything what burns fuel generates the pollution. So we are now really 100 years later in the similar situation that we must find a new system, new propulsion system with zero emissions. That is valid, of course, for cars, but also for aviation. So Airbus Helicopters, we were always on the top of any innovation. So first rotor with the swash plate, first turbine to generate the really useful load, first composite blades, press fenestron, which is still our sign of the company for helicopter below 5 tons, fly-by-wire. We are the only to use it on the NH90, and also our focus is very important for everything what is noise, and we work very hard on the noise, and the blue edge concept we use on H160 is really the latest revolution we introduce in this area. And you know, we live, I think, 3 kinds of revolutionary aeronautics. The first one, it was in 1940, where really the fixed-wing aircraft found the market. It was the flight from Tampa to St. Petersburg in Florida at 23 minutes of flight, $400, what makes $9,000 of today. And we found the first time the helicopter found the fixed wing, found the market, because people were able to go very quickly, 23 minutes. If they travel on ground, it would took a day. Yeah? And people playing stocks on the market or journalists found their business case paying this $400, which was a very significant amount of money, because there was the price of the speed. So the second revolution is roughly 1960, where we put the turbine on the helicopter, and this allowed to have really the useful load on the rotary wings. And the third one is this revolution we live now with zero emission flight. And this is, I think, the way we can really show every 50 years we live significant revolution in aviation. So Airbus Helicopters, we have now a really very clear roadmap to go to treat this revolution. We have the technobricks, which is the touches flight control, the digital, cyber, connectivity, avionics, towards all the technology towards zero emission propulsion, vehicle aerodynamics, and eco technology for the production. And what is our DNA are the demonstrators where we see here on the right, and we really love going quickly from the idea to the real life. So we have the flight lab. You could see in the press that we have flown just with the disruptive lab with completely new technologies. We have the Racer, which will go in flight this year. We have the urban air mobility CT Airbus new gen. We have flown already the first version. We have the drone. So this is really our roadmap going to zero emission flight. So nature, I will not stand much of it, but clearly everything is really to protect future generations and not to use the resources and not to pollute. So I think this is clearly the main target, and we have it in our DNA. So I will not put much in the equation. It's of course the only thing is the range of the flight is really proportional to the specific consumption of the vehicle, the drag. We must work on the drag, and of course reduction of the mass of the aircraft. The lowest mass of the aircraft, the best range we can get. So there are three main vectors: reduction of the mass with all the integration, reduction of the drag, because it is something fundamental. The coefficient to penetrate in the air must be the lowest possible, and the efficiency of the propulsion system, which is key, where of course hydrogen will play the role. So this is the roadmap. Okay, we go through for the zero emission flight. Okay, so we work on the vehicle aerodynamic. So this should bring from 10 to 15%. We are more in the region of 15%. Turbine with new aerodynamic cycle, which should bring something from 15 to 25%. We have also what will be tested on the Racer, the eco mode. We can switch off one engine in flight and to have another one to make our aircraft flying on one engine. And it's much more efficient to have one engine on the full power than two engines on the half power. Then hybridization will bring 10%. We can use, like in automobile, the batteries with the electric motors, and we can charge the battery in flight in some conditions and use it back on the aircraft in other flight conditions, and it gives significant 10% fuel burn savings. And all this techno breaks, which allow us to reduce the 50% of the fuel burn, and it opened the doors to new energies. Okay, it could be the SAF, sustainable aviation fuel, and of course the hydrogen, I think, is the main target. Today we do share the hydrogen. Why hydrogen? Hydrogen is 3 times more energetic, 1 kilogram, than 1 kilogram of kerosene, but it takes 4 times more volume. So key driver is really to reduce the energy we need to fly for flight, and this will allow in the second step to go to the hydrogen. This is the roadmap with concrete examples. We have flow with eco mode, what I was just explaining. We switch off one engine in flight, and we fly just on the full power on one engine, a reduction of 15 to 20%. It can increase the range. It can introduce the fuel burn. We have tested engine backup system on a Kuroi, which single engine helicopter, what allows improve strongly the auto rotation. And we were the first to test it in flight in the world. This is the first hybrid propulsion used on the rotary wing. Then we move very quickly. It will be mainly on the disruptive plot to the power hybridization, with the power put on the aircraft will be bigger, and we must go for this. This will, we currently started the flights on the flight disruptive lab, and this will be one of the important break of the disruptive lab. It will be the hybrid propulsion, and of course, company we decided to go to the zero emission flight. We have significant activity on urban air mobility, CT Airbus new generation. We have flown already 2 aircraft. It's the learning period, CT Airbus Alpha and Vahana, and this is the way we progress also in this fully 100% zero emission flight. Few words about the racer. To go quickly, we must have a very small drag. We use the box wing. Box wing allows to reduce the drag and also to put the landing gear in appropriate position. We have the pusher propeller, which are behind the wing. This pusher propeller allows to reduce 10% the fuel burn, because the box wing plays the role of the starter, and the energy we have behind the propeller is much less energetic, and we save the fuel burn. And well, this aircraft is built in the way like the fixed wing, okay, very long and very low drag, roughly 45% compared to the normal helicopter. And really the engine coolings are very performant to reduce the drag of the aircraft. And this is really something what allow to the rotary wing go to 220 knots, more than 400 kilometers per hour in affordable way. So this is way like single engine operation works. We have total fuel consumption. Here's the power. This is the curve showing the fuel burn as function of the power. More power we take, less we have the specific fuel burn. So if we have two turbines working on half a power, it's much better to have one working on the full power, because it will generate up to 25% less fuel burn, and it gives we can have 150 kilograms fuel saving for 400 nautical miles. So it's very, very important item. We can get 2 more passengers on the civil market, and of course much more capabilities on the military one. And this is a very, very interesting principle to use the high voltage start and stop system, because we must restart the turbine when really it is necessary. For this we use high voltage start and stop system. So this is the way the aircraft is now assembled. We will put we did the power on end of this year, and the flight will be in the second part of this year. We have this is the old picture, but the aircraft now is really 100% assembly process. A few words about the CG Airbus new generation. So we have 8 propellers. So there are, I think, 200 companies all over the world trying to do the UAM. We have our approach, which is based on the simple propellers, okay, which have no variable pitch, just variable RPM, because it's much more simpler. And really our approach is simplicity, and simplicity is basic, and aeronautics does not like complexity. So also we have very progressive approach. So we tested already CG Airbus Alpha, we tested Vahana, we do a lot of wind tunnel tests, theoretical simulation. We tested the propellers in the wind tunnel, that you can notice here, and we work very hardly also in the simulator, okay, to see all the failure conditions. So it's really very methodic approach, okay, that we can go for the UAM, which is difficult to be done by the startups, but this is the added value we can generate, the methodology to develop this kind of the rotary wings. Also, a fefew words, of course, why we fight so much for fuel burn reduction. So 1 liter of petrol generates 1.6 kilogram of the CO2. and it is due to the chemical reaction, and the oxygen is very heavy. So, and the problem of the CO2 is that when you emit it, you have 1,000 years in the atmosphere, so it's integral of everything what was done. So really, a reduction of this is key, because one emitted, it stays forever. Also, what is important, we will speak always about the energy, and this example is for the car, but it's exactly the same for the aeronautics. It depends how the electric energy is produced. Of course, if it is produced from the coal, it's of course even worse than to burn the kerosene. So it's when you speak about the energy sources, energy production, it's very important to have in mind the way the electric energy is produced. Just to show you the difficulty, okay, that if we make fully electric flight, 1 kilogram, 1 liter of petrol is roughly same energy like 27 kilograms of the lithium battery. So you can imagine it's not completely the same weight. It's very, very much more heavier. And so for the car, if you would like to have the same range, like the simple, let's say 1-ton car, what does it with 50 liters of petrol? It makes 500 to more than 500 kilowatt hours. We would need 2.6 tons of the battery. So you can imagine that on the electric car, we don't have the battery. And for the helicopters, it's of course even much more severe, because we take the simple one, which weight is 2 tons. To have the same range, we would need 24 tons of battery. So it shows you once again that electric flight is really for the shorter range, and the situation is much more challenging than in automobile. And now let's switch a bit to the hydrogen. Okay, so with the lightest element in Mendeleev table, just on the top on the left. Okay, and I will just remind few elements about this. Okay, which it means that 1 kilogram of hydrogen is 11,000 liters with 1 atmosphere. 200 bars is under 200 bar compressed is 65 liters. 700 bars is 27 liters, and for aeronautics, it must be liquid, okay, because already minus 250 degrees, it's 14 liters, okay, so it's 3 times more energetic, but it takes much more volume. So the first idea is, and first target is really to reduce the energy unit of flight, and we will, in the application for the rotary wing, it will be, of course, everything what is urban mobility, and of course, for the fixed wing is the regional aircraft, when the range is not so important. Over the, of course, the ocean, when the range is very, very high, the main application will be sustainable aviation fuels, because hydrogen will be too voluminous. Okay, a few words here about the hydrogen. If you have the mass hydrogen is one thing. If you use it hydrogen, but also the tank around. Okay, if you put it is very heavy, because for a few kilograms of hydrogen, we need a very heavy tank. Here for 5 kilograms of hydrogen, it makes the total weight of 87 kilograms. So hydrogen one thing, but where you stock it, because stock it to 700 bars, it requires the carbon reservoir, which are quite difficult to be produced and quite heavy. So when you speak about hydrogen, you should always have in mind the weight where it is stocked. Fuel cell, okay, it's something what we always have in mind. You know, fuel cell works in the opposite way to electrolysis. Electrolysis, we supply the current to the water and we generate the hydrogen. This electrolysis here is vice versa. We have the membrane in the fuel cell. We supply from one side hydrogen, air from other side. We have here the protons goes through the membrane, electron goes outside, and then we generate the electricity. And this electricity we send to electric motors, and then what generates the torque to the electric motors. So, and the one thing, just the message we tell it stocks from the fuel cell. The one thing also, the efficiency of the fuel is 50%, and we must cool 50% of thermal energy. So one important item from fuel cell is the cooling system. Okay, and this everybody should have it in mind. A cooling system, we might efficiency of the fuel cell is 50%, and the big challenge is have efficient exchanger to reduce the energy which goes from the heat from the fuel cell. Okay, of course, once again, the volume of the kerosene from A320. So clearly, the range we should have lower number of passengers because the volume of the tank will be bigger. So it's clearly the target to have it for the regional in the first step. One also important item of the hydrogen is way it is produced. Okay, because the worldwide production of hydrogen is really done from the gas coal, a crude oil. Okay, electrolysis, which is the clean one, is just 4 or 5%. Okay, so really we must now move. One is to make the aircraft available for the hydrogen compatible, but then also we must have the ecosystem to produce it, because actually only 5% is the electrolysis. So a lot of companies, you know, spent a lot of money to produce the clean hydrogen. So there is, I think, billions euros spent by Linde and Air Liquide to really produce the green hydrogen, and it is really a very important target. And also, you know, when we go from it is done for the car industry, which we have here the electricity, okay, produced, and from electricity we go to produce hydrogen, we compress it, we put it in the tank, we have the fuel cell, we have electric motor transmission. So
yes, sorry, Mr. Krysinski, to interrupt you. We are 8 minutes over time.
Okay, so
yeah, could you just wrap up a bit what you're gonna?
It's my conclusion. It's just the conclusion. You know, we are very happy that it's the last slide, and the Airbus is really sparked the revolution of the hydrogen, and somebody must do it in the one of them. So we are very proud to be the company who really initiated this idea. So it's all from me. I am happy to respond to a few questions.
Yes, okay. Since we heavily ran out of time, I think for now just one question from the audience, and if there are more questions, we would transfer it to you by email, and you could answer on that. If you got one question from the audience to Mr. Krysinski to Airbus helicopters, then we are ready to hear it. If not, no problem. We will transfer it by email to him, and he will answer it duly. Okay. If not, akkor most visszaváltanék magyarra. Thank you very much, Mr. Krysinski. Thank you.
Thank you a lot. Sorry to be longer.
It was a great lecture.
It's too passionate subject.
Yes.
Thank you a lot.
Thank you very much for being available.